So let's continue. Let's get to the point now where your software has your software's current functionality has been documented. Your initial tests are written. Where do you go from here? How do you improve your testing situation to the point where it's considered done? Let's think about the problem as selecting the right tests. So if you take a step back, there's levels of tests that are regression testing and CI type tests. The levels of tests might be something that's a continuous integration type quick diagnosis of error that you can quickly say if there's something going wrong, or if there's an issue with your source code or types or calling conventions. And then there's scheduled testing, which may be much longer running. This is particularly the case for scientific source codes, where you might have very large input files that are required to do some functionality test, or you might have very long running simulations which are testing the final output. Those can provide comprehensive coverage, but they'll take a little bit more time to run. Computer scientists tend to gravitate towards tests that run quickly and do these continuous integration types of things. And the domain scientists tend to think of ways to compare program outputs to external measures, like the golden file testing we talked about for known solutions, or example run cases. So you might actually have to split up your testing strategy into these two levels, do them two different ways. Since testing is so broad, individual tests can also vary in complexity. As a rule of thumb, complicated tests are bad because they don't let you go in and pinpoint exactly what the issue is. Tests should be as simple as possible, but always provide information on what went wrong. If a test can't help diagnose an error condition, then it's not a very useful test. So you want your test to be able to quickly pinpoint errors. So by the time you're testing against a golden file, you should have already tested a whole bunch of smaller things which would have caused that to error out. And if your golden file test breaks, we'll get to that a little bit later. Okay, why not always use the most stringent testing? You might be tempted to get overly creative and test everything that's possible into a test scenario. This can be counterproductive because the time that's spent on creating and maintaining and interpreting your tests takes away from team resources. Ideally, tests are closely aligned with the science objectives, and the tests themselves then provide some baselines and are motivating to create and maintain. If the testing goes too far away from that, it distracts your project. On the other hand, if there's not enough testing, then defects in your code can silently slip through. For example, users might assume the overlap region between processors is communicated correctly during a halo exchange. If there's no test that actually tries that out with varying halo size, there's no way to know when that assumption will break down. So the line of thought leads to the idea of a team meeting that's actually focused specifically on creating a testing plan. And the goal of that meeting is just to clearly map out the expected usage of your code, what parts of the code are critical to long-term stability, who on your team should be responsible for ensuring that each piece works, are there additional difficulties that come from the interactions between modules, and how can those be reasonably addressed with example use cases? Okay, so you've had the meeting, everyone is on board with your test plan, and your code is in a good place. What happens next? You can double check your work by using a code coverage tool like we talked about a little bit ago. You can create a policy on what to do with failed tests and issues marked as bugs. It helps to assign responsibility for moving those through the queue by reminding the product owners of the different pieces of your code, so that when things happen, that person will keep the resolution process moving along, but also that person gets recognized for being the person who is responsible for watching the tests go through. Cost effectiveness comes in here because if your test can help you with refactoring, when you have a good test suite that's already telling you a lot about your code, doing a refactor will help you to your tests will help you when you're refactoring, so that you know that as you're moving pieces of your code around, things still work. They also help you in supporting things once you've released them. Okay, with those general guidelines in mind, let's get down to some specific examples from the collective experience of our team members. Many of these examples come from Anshu Dubé's work with E3SM and the Flash codes. Example one is an ideal case where you're developing a new code and you develop your diagnostics as you're developing the code itself. Taking the extra time to harden those into a test suite will save you headaches later. You'll likely have a lot of comparisons against known expected solutions. You should try and make things as granular as possible, though, The scaffolding idea, discussed later, finds a way to build up a program, testing each new piece. Remember to inject errors into your tests so that you know your code will discover erroneous input correctly. As the package gets more complex, it's non-trivial to devise good tests. Nevertheless, good tests are extremely important. Proper testing procedures can also help encourage new contributors. Until recently, only recently I had this experience contributing a feature to the alpaca code, where the first thing I did was actually check out their code and run the tests on it. Everything was working before the tests, and there was already a test case there that pretty much matched the new code that I was going to add. So I was able to, of course, after telling the developers I'm going to add this feature, run the tests locally and make sure that it worked. And by the time I committed my new feature, I was pretty sure that everything was going to run fine, and that they would accept the code, and they were less anxious accepting a new contribution from an outside member just because they already had the tests in place. Okay, example 2, the probably best case scenario. Example 2 for legacy code. In a legacy code, there may not be existing tests. This is an example from, this example idea is taken from the E3SM code, the exascale Earth system model. Although advanced now, it actually originated as a combination of Fortran codes that dealt with various aspects of climate modeling. And as a combination of many modules, it was difficult to create an overall testing strategy. The testing strategy that actually ended up being useful is kind of documented here, and we can go through the steps for that, but it's based around isolating small areas of the code. So here, there is, say, a piece of the code over here that you want to test, but you can't quite test it without having its inputs and having all the other pieces of the code and functions that it can call on as it executes. So what was done was to isolate this small area of the code and look at what kind of state it takes as input and what its direct dependencies are, and to build a test driver. This test driver has the job of taking the current state, loading it up, and running it. What we're seeing with this red line is if there were external pieces that were accessed as these guys ran, then they were symlinked into this kind of isolated little area with the test driver. And if there were pieces that were not that were kind of used but not completely used, then some parts of the code could be rewritten as very small bits of functionality that were actually needed. Because this is a real test case, there were some external dependencies that became messy. This one was a symlink, and this one was a rewrite. Then finally, the test driver can load up the current state that was captured as this function was executing, and load in the state, exercise the piece of code, and result on its output. In this particular case, the original code took over an hour to run through on a batch queue of a cluster, but the new unit test ran in 20 seconds on a developer's laptop, just because creating this state was what was taking most of the testing time. And by creating a smaller test driver and doing isolated unit tests, then that could be run much more quickly. The third example comes from the Flash code, which simulates particles and fields in astrophysics, like exploding stars. Here, the unit testing framework was developed as a series of layers that build up from basic to advanced functionality. For example, the grid cell can be tested by creating fake functions to put into the grid and verifying their behavior. This mock dependency means that the test looks directly at the cell grid implementation and not so much at what functions are moving into and out of it. So you won't get an error with comparing to a golden file, because you're testing a known function that's a mocked up dependency. After you know that the grid cell is working by itself, then you can use that as a real dependency in subsequent tests of more complicated objects. That's illustrated by this graphic here on the right, where the mocked up dependency, like the function that's just a statically known test function that's mocked up, is used in order to test the grid cells. And now once those grid cells are present, or once the the functionality of putting a function onto a grid is tested, and your grid is tested, then you know that you can use that grid in larger scale tests. Here's another example of verifying the halo exchange process on a cell grid. This test initializes for halo cell test, like what I talked about at the beginning. What the test is going to do is initialize interior cells with a known function. And the exterior cells will be initialized to 0 or some random number. And when halo exchange completes, then information from the neighboring MPI ranks filled in cells will have copied into the halo cells of this MPI rank. So what's done is to initialize interior, fill these guard cells with zeros, run the halo exchange, and then check finally the halo area with the known function. And of course, once you've tested whether your halo exchange is working and you've tested that your grid cell fills are working, the next logical step is to add more pieces to your scaffold. So you can do an equation of state test that's testing whether or not on a single grid cell, energy as a function of volume and temperature is consistent with pressure as a function of volume and temperature, right? So you're looking at the models of the physics that are happening at each grid point. And once you've put all of those pieces together, you've got grid cell tests, you've got equation of state tests. You can do something that's even more high level, that's putting those pieces together. We can create, here I'm showing a test of the set-off blast wave, which is simulated using the grid cell fills and equation of state that are previously tested. The set-off wave has a known analytical solution which provides an error estimate of the implementation. And out of tolerance errors at this stage indicate a problem specific to the hydrodynamics, that is the movement of stuff between the cells, because we've already tested the other pieces, since the cells and equation of state are already tested. In addition, plotting errors versus space and time helps to train graduate students. These tests can be developed farther too. So even after you've tested that the set-off blast wave is correct, your code may go farther, and the Flash code goes much farther than that. It does non-uniform grid cells, so mesh refinement, and it can also do dynamic refinement, whereas the solution was forward in time, then the mesh refinement is also changing. And so if you just turn all those features on and you compare it with the golden file and it didn't work, you wouldn't have any idea where the error is. But here you can do this trick of comparing with the known solution after turning on each one of these features stepwise. So we do the testing scaffold first, and then we run the hydrodynamics without mesh refinement. And if it failed, we know that the problem was in hydro and moving stuff between the cells. After this is working, you can turn on adaptive mesh refinement, but not do dynamic refinement. And if you see a failure there, then you know that it has to do with fluxes between different sized cells at the flux boundary, at the boundaries. And then you can focus your development efforts fixing exactly what happened when you refined the mesh. And then finally, you can turn on dynamic refinement. And if you see an error at this point, you already know that all the other pieces of your physics and your code implementation are good, and you can focus your development effort in figuring out what about the regridding is causing your test to go wrong. The last thing that I want to talk about is how to map areas of your code for testing. We've already talked about code coverage reports, which give you line-by-line information, but it's often helpful to look at this from a functionality standpoint. In this chart, the x-axis is showing different kinds of physical models that are implemented in the Flash code, and the y-axis is showing functionalities of the code. So the equation of state, model might apply each one of these kinds of different functionalities. The way that the code coverage matrix worked is actually to go through all of the tests that they had and kind of survey them. First looking at the unit tests and ask what parts of the code are these unit tests exercising? Are they exercising, right, which one of these physics modules and which one of these features of the code? So the CL unit tests ended up exercising these, and so those were marked as checked by this unit test. Next, check the tests that are sensitive to perturbations, map which areas on the chart these correspond to. Then check the most stringent tests for the solvers, and then the least complex. Check the most stringent tests for the solvers, which are going to give you kind of coverage of these more difficult areas. If something is left remaining open here and you wanted to test it, for example, if you wanted to test particles in a multigrid situation, then you already know kind of where your tests are lying in this kind of physics versus computation space, and you can strategize about the right kind of test to fill in these gaps. And ideally, you want to pick a test that's the least complex, but it will still cover the remaining spots that are important. I say the areas that are important here because it's possible that you may never want to do hydrodynamics with, you may never want to do equation of states with FFTs. And in that case, it's fine that this is left blank. So this kind of coverage matrix is going to give you a high-level view that you can, a high-level view of your testing strategy that you can talk about with domain scientists and with the implementation team to make sure that you're covering the areas you need to cover. As high-level takeaways from this kind of advanced testing, it's important to understand the testing needs and the costs. So to know the context of your tests will tell you where you want to direct most of your effort and how you want to design them. You want to devise your tests as much as possible to allow you to quickly pinpoint the errors and allow you to reason about the code's behavior. And you can use this scaffolding approach that Anshu is really a big proponent of, where you start off with your unit tests and you build them up to much larger level tests so that you know that everything is good from bottom up. And you want to also think about different kinds of granularities and what kinds of integration, what kinds of validation you need to do on the integrations between codes units. Test at various levels of complexities. Some tests are better suited for short runs like that you can do continuously, and some tests are needed to be scheduled because they're longer running. And some tests are regression tests, which are looking backwards at previous bugs that you found and making sure that they don't recur. And so your testing strategy should be holistic and kind of consider all of these things and be a consensus that comes out from your team.